Okay, welcome to topic 2 electricity, lesson 4, resistance and resistance of a wire. So first thing we'll ask ourselves is, what is resistance? So I want you to imagine a wire, and inside we've got the electrons, the charges, and their job is to get from one side of the wire to the other. Now in the perfect world, it would be easy. There'd be no resistance to their motion. You give a little push and phew, they fly through. But in real life, it's not so easy, because in the way, obviously the wire is made of atoms. The atoms resist the flow of the electrons. And we call that resistance. So there they are. So each of those poor little electrons, as it's trying to get through, is moving and negotiating its way around the atoms, and that sum of the force is called resistance. So the first thing we can say is, if our little drawing is here, we'll call these the atoms, these are our charges, and if this was a minus side, because these charges are negative, they're going to want to go over to the plus side. Okay, that's why batteries have a plus and a minus. Okay, so we can say the charges flow. Now we call that current. So in future I'm going to use the word current. So the charges flow, current. The atoms, we'll do these as little bullet points. The atoms slow the current down. I'm going to sneeze. Bless me. The current slows, the atoms slow the current down. We call that resistance. Okay, so what is resistance? It is the action of the atoms slowing down the flow of the charges. So that's our final thing. The atoms slow the current down. Now, the chap who figured this out was called ohms. So he gave the unit as ohms. Now, you've got a problem here. If you write the number down, say this had a resistance of 5 ohms. 5. We can't do what Newton and Joule do. We can't write his first letter of his name, because all of a sudden everything looks 10 times too big. So George Ohms went through his bumper book of physics and he chose the Greek letter for O, which is omega. So that's its actual name, but we would say ohms. Okay, so 5 ohms. Now, how can we calculate the resistance of something? Well, it's very easy. We need two things. So to find the resistance, and I'm going to write the equation here, and as we've seen it's measured in ohms. To find the resistance we just need to know the voltage of the circuit, measured in volts, and we divide that by the current, which we measure in amps, like that. Now we can write it out as R is equal to V over I. Or, if we wish, we can put it in a triangle. The V is over the I, so V is going to go at the top. That means R and I go here, riv. And the other way of writing it down, if I wanted to use the triangle then to rearrange it into an easier form, is if I write it as V equals. So if I cover up the V, I get V is equal to I times R. And I'm saying it that way because I have a vowel in the middle. So I have V, I, R. Vir. That's how to remember it. Vir. V-I-R. Vir. Then you can put it in the triangle, rearrange it to make R the subject if you wish. And that's the equation. Right, I'm going to put that in a box, put it in a bright pink highlighter. That's the key equation of this lesson. Okay, highlight it. Now, we talked about resistance of a wire in the title. Knowing what we now know, we can actually go ahead and do a bit of an investigation. And here's the experiment. It's one of the required experiments that we do. And in this, we're going to look at what is the effect of making a wire longer. So, if I put required Required practical. Okay, I'm not going to try and do a line. Okay, and the question we're answering is, what does increasing the length of a wire do to the resistance of a wire? Okay, so we're going to make a wire longer and we're going to measure the resistance and we're going to see what that does. Now, the clue here is I've already got myself a ruler. That's, hey, put that back. Try that again. Is that going to take that with it? Crazy. Never seen that before. Let's see if I can just grab it. Nope. Okay, that's going to have to stay. So, here's how we're going to do it. Let's put down what our variables are. So, our independent, all the E's, our independent variable is going to be the length. Okay, length of wire. Independent, I'm going to change it. Our dependent, all the E's again, dependent, is going to be the resistance. And things I'm going to keep the same, so controls, are the wire and the temperature. And we'll talk a lot more about the temperature later. Temperature of the wire, I mean. Okay, so on to why I've put this ruler here. What we have is we have our cells, our battery of cells. We connect it up to the 0. So we go up like so. And we put a crocodile clip on it. So crocodile clip on 0 as best we can. Okay, now straight away you can see, look, didn't put it on 0. So that's a really big issue in this experiment. So I'm going to clip it, there we go, to as close to 0 as I can get it. There. Next, on this one, I'm going to measure the current. So I'm going to put an ammeter in. And then I'm going to complete the circuit by clamping it. And I'm going to go, in this case, I'm going to start at 10 centimeters. Like that. And again, I put my crocodile clip on it. And again, look, I'm not quite on it. How could I get closer, I wonder? So I've measured the current. And then there's one last thing I need to measure, and that's the voltage. Like so. And so what I'm going to do is make a little table where I have length. And I can measure it in centimeters, it doesn't matter. I'm going to have voltage in volts. I'm going to have the current in amps. And from that, I can use Ohm's law, voltage divided by current, to make a table with resistance on it. And that's my end goal. Remember, the dependent variable was resistance. So if I just move that across a little, make some space, go across here, figure out how long I want to make it, and then go across, and then I can have resistance. And remember, it's measured in ohms. There we go, the perfect table. Next, with this experiment, you don't want to go shorter than 10 centimeters. Reason being, the current will fly through, it will set fires. So we start at 10. We're going to go up in 10 centimeter intervals, 30, 40, all the way up to 100. Okay, so 1, 2, miss a few, 100. Obviously, if we were doing this in real life, we would mark each one out. Next, we'll record the voltage. So I'm going to make this up, 10 volts for each one. Keep it nice and simple. Okay, 10 volts. And with the current, we find that, a bit like playing rugby, if you've got a dash, if you've got the ball and you're really close to the line, you know, if every game started with you already just 10 meters away from the finish line, you're going to get over really easy. However, what happens if we now make it further away? As we make the goalposts further away, it's getting harder and harder to get there, because unfortunately there's always the other players. These are the atoms. And so as you're trying to float, you're the little electron, you're having to dodge and swerve, and it gets harder and harder to get over the finish line. And the same is true here. So our first result for current is going to be the biggest number we are going to see. So let's put 5 amps. Now let's use Ohm's law. Ohm's law is resistance is voltage divided by current. So we're going to have 10 over 5 is 2 ohms. Next, we straight away see when we double the length, it's twice as hard to get through. 4. Then it happens again. 6, 8. And so going down, we see that the resistance increases more and more, to the point where when we get to here, we might have, I'm trying to now estimate, 0.5, which would be 20. And if we plot that as a graph, let me get rid of my little rugby game a minute, wipe out the players. If we plot a graph, we get the straightest graph you ever see in an experiment, if you've done it correctly. Along the bottom, we have length in centimeters. That's the one I'm going to change, my independent. Let's color code it. I'll do it in red. Length of wire. Always goes along the bottom. Look, there it is there. Always goes along. Then, the dependent variable, the answer, is always the last one there, and it goes up the side. So resistance in ohms, like so. And what we see, without having to draw the numbers in, is the straightest line graph you've ever did see. So all my numbers, I'm going to cheat, all my numbers will lie upon this line. So what we can say is, in our conclusion, we can write the resistance is, now I'm going to use a phrase when you have a relationship like this. It's a straight line and it's going through the origin. And if I doubled it, I doubled the other thing. So if I went from 10 to 20, I doubled it. I went from 2 to 4. Okay, so times 2 and times 2. So a relationship like that is called, I'm going to write it big, directly proportional. Directly proportional. I'm going to straight away, before I forget, put it in bright pink because it is such a key point. The resistance is directly proportional to the length of wire. Okay, I'm going to just embellish a little bit more here. You just remember I said it was a straight line graph, and it went through the origin. So through origin. That is the definition of a directly proportional graph. Okay, you can be explicitly asked that. So I've seen exams where they've said, tell us 2 things about a directly proportional graph. Alright, so learn them a lot. Straight line and through the origin. Now, we talked at the beginning, when we talked about controls, I'm going to do those in green. Controls, we said the wire, obviously you don't want to change type of wire, that kind of stuff, but also the temperature. So there's a really key part to all of this, and it is this. The wire runs along here. There it is. I forgot to mention that. Let's draw it in orange because it's a wire. Okay, it's like, well, how's he conducting through a piece of wood? There was a wire sellotaped to the ruler. Forgot to mention that. So the current will go obviously through here, up here, through the wire, down through, record the current and back, and it'll just go around like that. Now, if we put the wire too short, there will be a flood of current getting through, and the wire will start to get very, very hot. You don't want that for 2 good reasons. Obviously, the first reason is you don't want to burn. So I'm going to put the subheading here, heating. Heating wire. Okay, and we're going to just list 2 reasons. 1, danger. So danger of burns. Okay, that's the first thing. Don't want to get burnt. Go home with a branding of a straight line across you. The other thing is, go back to my idea again of playing rugby. Okay, we've got our atoms. Here they are. They make up the atoms that are in the wire. There's my little electron. He's got to get through. When the wire is cold, the particles are vibrating, but just a little bit. It's very easy to get past. But as the current goes up, they're bashing into each other, they start to vibrate more. The next charge to get through has a really hard time. So the resistance is increasing with temperature. So let me say that one more time. The atoms in the wire are vibrating all the time, even when they're at like 0 degrees, right? But just tiny little vibration. As more current flies through, bash, 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 the atoms start to vibrate more and more and more. And so the wire gets hotter and hotter. And if they're jiggling around like that, let's just draw some little jiggle vibrations. Now imagine trying to get past a rugby team that's all hyped up, that they're full of energy, they've had a good rest. And so this time the rest of the current trying to get through is having a heck of a time of it. So it would describe it as the resistance increasing with temperature. So that's our second one about the heating. Hot wires have more resistance. What would this mean? It would make the experiment. Now, when you keep one thing changed, length of wire, you measure the other thing, but you control everything else, that's called a valid experiment. This will be an invalid. So, hot wires have more resistance. They make the experiment invalid. Because now you've changed 2 variables. You've changed the temperature and the length. And that's not what we're investigating. You could do that by heating the wire up, but then you would need to keep the length of the wire the same. And that's not what we're investigating today. Okay, so that concludes this lesson. Hopefully you've got all the notes. Use your textbook to cross-reference it. There's quite a lot in this one. And any questions, put them in the comments. Take care. Bye.